Somewhere in the colony, a small pump is failing. Not dramatically, just a worn seal, a part smaller than your thumb. On Earth, replacing it would take a single phone call to a supplier, but this colony has no Earth left to cool. And behind that one tiny seal stands something the colonists never packed. The mines, the smelters, the factories, the chemists, the machinists, the hospitals, the universities and entire planet's industrial and medical web, hidden inside every spare part they ever used. The food shipments were never the real lifeline. The lifeline was the civilization that quietly built everything that kept them breathing. So here is the question we're going to chase. Once that hidden web is gone, how long can people truly survive on what they carried? If you enjoy these kinds of videos, consider tapping the like and subscribe button. I appreciate everyone who supports this channel. Now, settle in and get yourself comfortable. Let's begin. Let's go back to that pump. It sits somewhere deep inside the colony's life support core, bolted into a rack of humming hardware that almost nobody thinks about, because for years it simply worked. It moves fluid through a loop coolant, or wastewater, or the brine left over after the colony's recyclers have wrung every usable drop out of it. The pump is not glamorous. It does not appear in the recruitment posters. But it runs quietly for 10,000 hours, then 20,000, and then one ordinary afternoon a single seal inside it gives up. The seal is a ring of synthetic rubber, engineered to survive heat and pressure and chemical attack. It has been flexing a few times a second for years. Now it has hardened, cracked, and begun to weep. Pressure drops. An alarm chirps. A technician pulls the unit, opens it, and finds the failure in about 90 seconds. The diagnosis is easy. The repair is impossible. Because to repair it, you need a new seal, and there are no new seals. This is the moment the whole story turns on, so let's be precise about what we mean. When we say a colony lives without Earth, it does not mean Earth was destroyed, and it does not mean the food trucks stopped coming. It means something narrower and far more unforgiving. No resupply, no replacement hardware arriving on the next ship, no emergency evacuation if things go wrong, no imported medicine, and no guarantee that the one person who understands a given system is still alive, or was ever there at all. Cut every one of those lifelines at once, and the colony is no longer a remote outpost of human civilization. It becomes a closed box, and everything it will ever have, it already has, or it must somehow make for itself. So the colony cannot phone a supplier. It cannot wait 6 weeks for a cargo ship. It has exactly one option: open a storage locker and pull out a spare seal that someone, years ago, had the foresight to pack. And maybe there is one. Maybe there are 5. But here is the quiet arithmetic that decides everything. A spare is a finite object. Once you install it, the count drops by 1. The colony is not generating new seals. It is spending down a horde. And the day the last spare goes into the last pump, the colony has not solved the problem. It has only postponed it. Now look closely at the thing that failed, because the seal is going to teach us how deep this goes. It looks like nothing, a flexible ring you could close your fist around. But that ring is a precise blend of fluorinated polymers, chosen so it stays elastic across a punishing range of temperatures and shrugs off the chemicals it bathes in. Those polymers come from petrochemical feedstocks, refined and reacted in industrial plants the size of small towns. The exact formula is the product of decades of materials science. To make one from scratch, you would need the raw hydrocarbons, the chemistry to build the polymer chains, the additives that give it its character, a mold machined to a tolerance finer than a hair, and the curing process that turns a gummy paste into a part that will survive 20,000 hours of abuse. Miss any step, and you get a ring that looks correct and fails in a month. There is a famous little essay from 1958 that makes this point better than any lecture. It walks through everything required to produce a simple wooden pencil: the cedar, the saw, the graphite, the lacquer, the brass, the eraser, and it arrives at a startling conclusion. Not a single person on the entire planet knows how to make a pencil by themselves, start to finish. The knowledge is smeared across thousands of people who will never meet. in mines and mills and factories scattered around the globe, none of them aware they are collaborating. A pencil is the product of a civilization, not a craftsman, and if that is true of a pencil, sit for a second with what it means for a sealed precision pump, or a power transistor, or a medical scanner. That is the hidden machinery promised at the very start. The seal is not the problem. The seal is the visible tip of something enormous and buried. Behind it stretches a root system that reaches down into the entire industrial body of a planet. To make that one ring on demand, forever, the colony would need, somewhere in its possession, the equivalent of an oil refinery, a polymer chemistry lab, a precision tool shop, and the accumulated expertise of an industry that took Earth a century to build. The colonists packed the seal. They did not pack the civilization that makes seals, and almost nothing they rely on is any simpler. Every valve, every circuit board, every sensor, every bearing, every lubricant, every gasket carries the same invisible debt to a planet they can no longer reach. If that sounds abstract, we already have a real example of how this plays out, orbiting overhead right now. The International Space Station is the most self-contained habitat human beings have ever operated. It recycles its water, generates its own oxygen, scrubs its own air, and keeps people alive in a vacuum that would kill them in seconds. If anything humans have built deserves the word self-sufficient, it is that station. And it is not even close. The International Space Station is resupplied constantly several times a year by a rotating fleet of cargo ships. Those ships bring fresh filters, replacement pumps, new chemical beds, spare parts for the spare parts, food, and the steady trickle of consumables that the recycling loops cannot quite recover. When a critical component fails up there, the standard fix is not to manufacture a new one in orbit. It is to fly one up, or in the worst case, to bring the crew home. The station survives not because it is independent, but because it sits at the end of a supply line a few hundred kilometers long. Pull that line, and the most advanced closed habitat we have ever flown would begin, slowly and certainly, to run down. And the part of that station most often praised as a triumph of closure is exactly where the trap hides. Consider its water. For years, the station recovered somewhere around 90 to 93% of its water, reclaiming moisture from the crew's breath and sweat, and distilling drinkable water back out of urine. Then engineers added a new device, the brine processor assembly, which goes after the last stubborn bit of water trapped in the leftover brine. With it, total water recovery climbed to about 98%. The team that runs the system put it plainly: collect 100 pounds of water, lose roughly 2, and the other 98 just keep going around and around. That is a genuine engineering marvel, and it is exactly the kind of number that gets a colony killed if you misread it. Because 98% recovery does not mean the water system is self-sufficient. It means the water system is very good at recycling, which is a completely different thing. And the difference is the whole point of everything that follows. That loop runs on hardware. It runs on a distillation assembly with moving parts that wear. It runs on a stack of filters and chemical beds that gradually clog with minerals and biological film and have to be swapped out on a schedule, roughly every year or so, or the whole loop fouls and chokes. It runs on pre-treatment chemicals, among them chromium trioxide and sulfuric acid, that have to be dosed into the urine before processing to keep the equipment from precipitating solids and destroying itself. Those chemicals are consumables. They get used up. They come from a factory. On the station, when the filters clog or the chemicals run low, a ship brings more. In a colony without Earth, no ship comes. The recycling rate is still 98%. But the machine doing the recycling is wearing out, and the chemicals feeding it are draining away, and there is nothing behind them. This is the distinction to hold on to, because everything else here flows from it. Recycling means looping your resources back around, so you lose only a little each time. Self-sufficiency means being able to replace the looping machinery itself, forever, with no help from outside. A colony can recycle almost perfectly and still die, because recycling buys you time, while only self-sufficiency buys you a future. The water keeps cycling right up until the day the distillation assembly seizes, and there is no replacement and no shop to build one. At that instant, the 98% becomes zero, not gradually, but in a single failure. The number was never the thing keeping them alive. The supply chain behind the number was So the obvious answer rises up immediately. Just make the parts. Bring the tools, bring a workshop, and manufacture replacements as you need them. And this is where the flaw drops out, because making parts pulls you into one of the deepest holes in all of engineering. To make a precision seal, you need a mold cut to extraordinary tolerances. To cut that mold, you need a machine tool, but that machine tool has its own bearings, its own motors, its own control electronics, its own cutting bits that dull and must be replaced. To make those, you need other machine tools. To make those, still others. Industrial civilization is built on a tower of machines that make machines that make machines, and almost no level of that tower can recreate the level above it from raw materials alone. You cannot bootstrap a semiconductor out of a lathe. You cannot grow a lathe out of a furnace. Each tier demands the tier above it, and the colony, no matter how much it packs, has carried only a thin slice of that tower with it into the dark. And there is a particular cruelty hidden inside that machine shop, one that turns the colony's last hope of self-repair against itself. To shape metal, you need a tool harder than the metal you are shaping. A cutting edge, a drill, a die, a grinding wheel. But the act of cutting is also the act of destroying the cutter. Every pass a blade makes across steel wears its edge a little duller. Every hole drilled blunts the bit. Every part stamped deforms the die a fraction more. The tool that makes everything is itself consumed by making it. On Earth, this is invisible, because replacement cutters arrive by the box. The colony has no box. Its cutting edges are made of tungsten carbide, of hardened alloys, of ceramics, sometimes tipped with industrial diamond materials chosen precisely because they are among the hardest substances we know how to make, and therefore among the hardest to make at all. To produce a fresh cutting tool, you need an even harder process to shape it, and abrasives to sharpen it. And those abrasives wear out too. A worn edge does not simply stop working. It works badly, cutting rough and imprecise, dragging the colony's parts steadily, invisibly, further and further out of true, so that even a settlement that still owns its machines slowly loses the sharpness those machines depend on. You can carry a lathe across the dark. You cannot carry an endless supply of the edges that make a lathe useful, and a lathe with nothing sharp left to cut with is just furniture, and the molds and dies are worse, because they are not general purpose. A cutting blade can shape many things, but a mold that casts one specific component casts only that component, and casting after casting it degrades, the surfaces erode, the fine detail softens, the dimensions creep until the parts it produces no longer fit. To make 100 different replacement components, the colony may need 100 different precision molds, each one a difficult object in its own right, each wearing out on its own schedule, each impossible to replace once the means of cutting fresh ones has dulled away. So the workshop the colony was counting on to save it is not a fixed capability at all. It is a stack of consumables disguised as machinery edges that blunt, abrasives that exhaust, dies that wear quietly spending itself down every time it is used to fix something else. The very act of repairing the colony consumes the colony's ability to repair, and it gets worse the moment you remember electronics. Almost every system on which the colony depends is run by a microcontroller, a chip with circuit features measured in billionths of a meter, etched into silicon inside a fabrication plant that costs billions of dollars, consumes ultra-pure water by the ton, and requires a clean room engineered to be thousands of times cleaner than a hospital. There is no tabletop version of this. There is no rugged field unit a crew can run in a habitat module. The entire planet has only a handful of facilities capable of making the most advanced chips, and they represent one of the most concentrated, fragile, and irreplaceable capabilities our species possesses. A colony that loses its supply of microchips cannot etch new ones in a side room. When the controllers begin to fail, and electronics do fail, from radiation, from heat cycling, from age, the colony has spares, and then it has fewer spares, and then it has the same problem as the seal, except now it is the brain of the life support system that is going dark. This is the right moment to be honest about the technology people always reach for as the rescue: 3D printing. Manufacture parts on demand in place, and the spare parts crisis dissolves. It is a real capability, and it is genuinely promising, and it is nowhere near as powerful as the dream suggests. Let's separate what is operating right now from what is hype. Operating right now, today, in orbit. Plastic 3D printers that can extrude tools and small components from spools of polymer feedstock. Among the first things printed in space was a small ratchet wrench. Back in 2014, a real and historic moment. Operating right now. Recycling units that grind up used plastic and old printed parts and turn them back into fresh feedstock. Closing a small loop so the crew does not have to carry endless spools of raw material. Those systems exist and they work. Demonstrated, but only at the very edge, at limited scale. Metal. In 2024, engineers achieved the first 3D printing of a metal part in orbit, using a laser melting printer about the size of a kitchen microwave that had to be carried up in pieces and reassembled by the crew. That is a real milestone and it matters. But it is one small metal part, printed once, as a careful demonstration, in a machine that itself is full of lasers and optics and electronics that no colony could repair from scratch. Still on the drawing board, under active development but not solved, printing functional electronics, circuits, sensors, the connective tissue of any complex machine, and firmly in the realm of pure extrapolation, not demonstrated anywhere by anyone. Printing a working microprocessor, a sealed electrolytic capacitor no bigger than a grain of rice, a precision ball bearing that holds its tolerances, or a flexible chemical-resistant seal that survives 20,000 hours. A printer can give you a bracket. It cannot give you a brain. There is one more catch that rarely makes the headlines, and the engineers who run these systems keep raising it. Even when you can print a part, you then have to trust it. On Earth, a manufactured component is inspected, stress-tested, certified, backed by an entire quality control apparatus that exists precisely because a hidden flaw can be lethal. A part printed in a habitat, layer by layer, in conditions the original designers never tested, might look perfect and carry an invisible weakness, a void, a bad bond, a microscopic crack. The colony has no certification lab, no fleet of test articles to destroy in trials, no margin to discover the flaw the easy way. So even the parts they can make, they cannot fully trust. And trust is its own kind of supply that Earth quietly provided and the colony cannot import. There is a useful way to split everything the colony owns into two piles, and the split decides how each thing will eventually kill you. In one pile sit the durable goods, the pumps, the structures, the tools, the reactors. These are built to last, and when they fail as objects you can, at least in principle, repair or rebuild. In the other pile sit the consumables, the things designed from the very start to be used up and discarded. Filters, chemical beds, pretreatment fluids, lubricants, gaskets, adhesives, sealing compounds. And here is the quiet bias that catches every colony. The human instinct is to guard the durable goods, the big, expensive, obvious machines, while the consumables drain away in the background, unwatched, because each one is individually cheap and forgettable. Yet it is almost always the cheap, forgettable, used-up thing that runs out first. A settlement does not lose its power plant in the first decade. It loses the specialty grease that kept 100 small mechanisms from grinding themselves into ruin, and the power plant simply happened to be downstream of the grease. So start with that grease, because lubricants are the quietest killers on the entire manifest. Between any two pieces of metal sliding against each other lies a film of oil thinner than a sheet of paper, and that film is the only thing standing between smooth motion and a seized, welded wreck. Every bearing, every hinge, every gear, every valve stem, every door mechanism rides on it. A complex facility does not need one lubricant, it needs dozens, each formulated for its exact task. A light oil here, a heavy grease there, a special non-reactive compound somewhere else. And each one is a petrochemical product, as intricate in its own way as the seal we began with. And lubricants do not last. They cook and break down under heat. They creep and migrate away from where they are needed, especially in low gravity, where there is nothing to hold them in place. They collect grit and turn from protector into abrasive. They thin, they harden into varnish, they slowly boil away into vacuum, You cannot wring fresh, high-performance lubricant out of a colony's farm or recyclers. And when the right oil finally runs dry, the mechanism it protected does not coast to a gentle stop. It tears itself apart and it drags the durable machine, the one the colony was so careful to protect, down with it. Then there is a stranger enemy, one that exists only out here and waits patiently inside every joint: cold welding. On Earth, every metal surface wears a thin, invisible coat of oxide and grime that keeps it from bonding to the metal beside it. In the hard vacuum of space, that coat can be scrubbed away, and when two clean bare metal surfaces of the same material are pressed together, they can simply fuse weld themselves into a single piece with no heat at all, because to the atoms there is no longer any boundary between them. A mechanism meant to slide or rotate can quietly seize into a solid lump. And alongside this sit the humblest items of the whole settlement, the ones nobody even thinks to count: the fasteners and adhesives, the bolts and clips and glues and tapes that hold every structure together. Bolts loosen under years of vibration and fatigue until they shear. Adhesives age, embrittle, and let go. A structural epoxy that has waited too long in storage may refuse to cure at all. These too are products of chemistry. The colony cannot reproduce the exact alloy of a high-strength bolt, the precise formula of the adhesive bonding a pressurized wall. A settlement can have a working reactor and a full pantry and still slowly lose the ability to securely join one thing to another, which is a strange and undramatic way for a place to begin coming apart. But the deepest hole in this entire first act is one we have not yet touched, and it lies underneath the whole dream of manufacturing replacements: the problem of measurement. To make a precise part, it is not enough to own a tool that can cut metal. You must know, to within a fraction of a hair, that you have cut it correctly, and that demands a reference to measure against. A master gauge, a standard, and this is the trap that catches everyone, because the reference is itself a physical object, and physical objects drift. A measuring instrument wears, warps with temperature, and loses its accuracy with age, which means it must be checked against a more accurate reference, which must in turn be checked against one more accurate still. On Earth, that forms an unbroken chain of calibration reaching all the way down to the fundamental constants of physics, maintained by national laboratories whose entire purpose is to keep the world's rulers honest. The colony carries the top link of that chain, and none of the vast institution beneath it. Slowly, silently, its standards drift. Its ability to measure decays, and a colony that can no longer measure accurately can no longer manufacture accurately. Its parts begin to come out subtly wrong, fitting a little worse with each passing generation, tolerances creeping outward, until the very precision the whole settlement is built on has quietly bled out of its instruments without a single tool ever breaking. You do not need to lose your machines to lose the ability to make things. You only need to lose the ability to know whether what you made is right. And then there are the electronics, which deserve a second and harder look, because earlier we treated them as things that simply break, and the truth is stranger and far more relentless. Electronic components do not only fail when stressed. They die on their own, slowly, even sitting idle and untouched, by several separate mechanisms working at once. The capacitors that smooth the flow of power in nearly every circuit are often filled with a fluid that gradually dries out over the years, until one ordinary day, the component quietly stops doing its job. Solder joints, flexed by a decade of heating and cooling, grow microscopic cracks until a connection that worked perfectly for years simply opens. In certain materials, thin metallic filaments grow on their own across a circuit board over time, and shorted out a failure mode that genuinely took the wider engineering world by surprise when it first began killing hardware. And over all of it falls the steady, invisible sleet of radiation, flipping a bit here, weakening a transistor there, accumulating damage in silicon that was never built to be repaired. There is no fixing this at the level that matters. A technician can swap a whole board, if a spare board exists, but no colony can reach inside the chip and repair the dying transistor, any more than it could etch a new chip from scratch. So the colony's electronics are not the stable foundation it can lean on while it wrestles with its mechanical troubles. They are dissolving quietly on their own schedule, whether anyone touches them or not, and they are precisely the part of the settlement that the settlement is least able to remake. Put all of this together and a shape emerges, and it is not the shape people expect. The colony does not face one big switch labelled survival that flips off on a known date. It faces thousands of separate clocks. Every critical component, every pump, valve, seal, bearing, board, sensor, and chemical bed has its own mean time to failure, its own expected lifespan before it wears out or breaks. Some last decades, some last months. The spares for each one are a finite stack. So the colony does not fail all at once. It fails one part at a time, quietly, on a schedule no one can see in full, as each little clock runs down and each stack of spares empties. The real question, the question everything here is built around, is brutally simple. Can the colony remake what it loses faster than it loses it? For some parts, the answer might be yes. A bracket cracks, they print a new bracket, life goes on, and that failure is recoverable. For others, the answer is a flat no. The last sealed controller dies, there is no way to etch another, and that single failure does not just break a machine. It starts something that cannot be reversed. And notice what that means for how the end would actually arrive. It would not look like an explosion. It would look like a colony quietly running its inventory down a settlement that appears to be working perfectly. Lights on, loops cycling, people going about their days, while the count of irreplaceable spares ticks lower in a storage room. Nobody visits. The countdown is already running the instant the supply line is cut. It is just silent. And the colonists may not feel it for years because the first failures are easy and the spares are plentiful, and the recyclers hum along at 98% and everything seems fine. But here is the thing that should keep you watching. Everything we have talked about so far, the seal, the pump, the chip, the printer, the whole tower of machines that make machines, all of it, is the part of the problem you can hold in your hand. It is mechanical. It wears out. You replace it. And as long as you can replace it, you survive. That is the simple half of the question. Because the colony is not only a machine, it is also alive. It breathes, it eats, it grows food. It processes its own waste back into the air and water that keep it breathing, in a loop far more intricate than any pump. And that living loop does not just wear out, it leaks. Quietly, every single cycle, it loses something, not a part you can print, but atoms you can never get back. Which means the next failure we have to understand is not a broken machine at all. It is the slow, invisible bleeding of the very elements that keep a body alive. Watch a single carbon atom for a moment, because its journey is about to explain why a colony can do everything right and still slowly starve. It begins inside a grain of wheat growing in the colony's farm. A colonist eats the grain. Their body breaks it down, pulls the energy out of it, and exhales the spent carbon as carbon dioxide into the cabin air. The air handlers sweep that carbon dioxide up. Some of it is fed to the plants, which breathe it in, stitch it back into sugar using light, and lock it once more into a grain of wheat. Around and around it goes, body to air to plant to body, a loop so elegant it can feel like perpetual motion. And that feeling is the most dangerous illusion in the entire colony, because the loop is not closed, it is merely tight. Every lap around the circle, a few atoms slip out through a crack you cannot see, and they do not come back. This is the heart of the biological problem, and it is a completely different kind of threat from the one we just left behind. A moment ago, the enemy was where? Parts that break and must be replaced. Here the enemy is leakage, matter that quietly escapes the loop and is gone for good. A broken pump is a discrete event. It fails, you notice, you react. A leak is a slope. It never triggers an alarm. It simply runs in the background for years, draining the colony of the specific atoms a human body cannot live without, while every gauge on the wall reads normal. To understand how a thriving settlement could be dying without knowing it, you have to understand the difference between recycling something and truly closing the loop on it, and you have to understand that biology, by its nature, leaks. Start with the cleanest case, the one the colony will be proudest of. Water. We already met the number, roughly 98% recovery, the best closure ever achieved on the International Space Station. Hold that figure up to the light and ask what the other 2% is doing. 2% lost per pass sounds trivial, almost rounding error, but a closed colony does not run the loop once. It runs it continuously. cycle after cycle, year after year. And loss is that small compound in a way the human mind is terrible at feeling. Imagine the loop turns over its entire water supply many times across a year. Lose 2% on every single turn. And you are not losing 2% a year. You are paying that toll again and again and again. The water that vanishes does not evaporate into nothing. It gets locked into places you cannot easily get it back from. It is trapped in the brine sludge the recyclers cannot fully wring out. It is bound into the bodies of growing plants and the structure of waste solids. It is vented to the outside as vapor every time an airlock cycles or a seal breathes. None of those losses is a catastrophe. Added together, over years they are a slow withdrawal from an account with no deposits. Now widen the frame, because here is the insight that reorganizes everything. In a living habitat, air, water, food and waste are not four systems. They are one. They are a single coupled chemistry, and you cannot tug on one strand without moving all the others. The carbon you exhale is the carbon a plant needs. The water a plant transpires is the humidity your dehumidifier reclaims for drinking. The nitrogen in your urine is the nitrogen a future tomato is desperate for. Waste is not a category to be disposed of. In a true loop, waste is simply food that has not yet been routed back to the right mouth. The colony does not run a water system and an air system and a farm. It runs one enormous interlocking metabolism, and like any metabolism, it lives or dies on whether every element gets returned to its place faster than it drifts away. Take the air, which the colony cannot survive without for more than minutes. Oxygen does not come free even when you have water. The standard method is electrolysis. Run electricity through water and split it into the oxygen you breathe and hydrogen as a byproduct. Fine. But now you have a stream of hydrogen and a cabin filling up with the carbon dioxide the crew exhales, and you would like to recover both. On the International Space Station, this is where a clever bit of chemistry comes in, a reaction named for the chemist Sabatier, pronounced Sabatier, which combines that waste carbon dioxide with the waste hydrogen to regenerate water and produce methane. The recovered water goes back into the loop. Lovely. Except the methane, which contains carbon, the crew exhaled, and hydrogen split from precious water is typically vented overboard. Every breath that follows that path leaks a little carbon and a little hydrogen out of the colony permanently. The station accepts this because a cargo ship will replace what is lost. The colony cannot. So even the air loop, the one we treat as the model of closure, is quietly hemorrhaging two of the most important elements in the human body, exhale by exhale, forever. If you want proof that this is not theoretical hand-wringing, history already ran the experiment, and it nearly suffocated 8 people. In the early 1990s, in the Arizona desert, a project called Biosphere, 2 sealed 8 humans inside a giant glass and steel world stocked with a miniature rainforest, an ocean, a farm, and thousands of species, and tried to make it self-contained for 2 years. The water cycled. The plants grew, and then, slowly, the oxygen began to disappear. The level in the air fell from the normal share of roughly 21% down toward 14%, low enough that the crew grew exhausted and sick, struggling to finish sentences until the project finally had to pump oxygen in from outside to keep them safe. The cause was a subtle, invisible leak nobody had modelled. The concrete in the structure was absorbing carbon dioxide, and the microbes in the rich farm soil were consuming oxygen faster than the plants could make it. 8 smart, well-prepared people in a sealed world were betrayed not by a dramatic failure, but by an atomic imbalance they could not see until their own bodies started failing. That is the signature of the leak. It does not announce itself. It just bends the slope down while everyone insists things are fine. So if water is hard and air is harder, the truly punishing loop is the one that has to deliver all of it at once, plus everything else a body needs, food. And food is where the gap between recycling and self-sufficiency becomes a chasm. Here we have an honest, sobering benchmark. The European Space Agency has run a closed-loop bioregenerative project for decades, named the Melissa Project, built to mimic the way a lake recycles waste into life through a chain of microbes, algae, and plants. Its pilot plant is the most serious closed biological loop ever assembled. And after all those years of work, what can it actually sustain? Roughly one person's worth of oxygen, and somewhere between 20 and 40% of one person's nutrition. That is not a criticism of the project, which is brilliant and patient science. It is a measurement of how staggeringly hard the problem is. The most advanced closed food and air loop humanity has built keeps a fraction of a single human fed. A colony of hundreds must close what we have barely closed for one. And before we even reach the chemistry of why food is so hard, there is the raw physical scale of it, which is staggering on its own. A human being is not fed by a windowsill of herbs. A person eats roughly 0.5 kilogram of dry food every day. And to grow that from scratch under artificial light takes a startling amount of the two things the colony can least afford to waste: area and power. Feeding a single colonist from crops can demand tens of square meters of intensively lit growing space. And lighting that space means pouring electricity into it hour after hour. Because out here the plants are not basking in free starlight. They are drinking watts, the same watts every other system is fighting over. Multiply that by a settlement of hundreds, and the farm becomes the single largest consumer of energy and volume in the whole colony. An enormous glowing engine that must never be switched off, because the day the lights dim is the day the food supply begins to die. Then there is the matter of breathing in time with the plants, which sounds poetic and is actually a control problem that can suffocate you. The crew exhales carbon dioxide and inhales oxygen, day and night, without pause. The plants absorb carbon dioxide and release oxygen, but only while they are lit, and only at rates that rise and fall with their growth. The two rhythms do not match. A crop newly harvested stops producing oxygen all at once. A crop in darkness consumes it. So the colony cannot simply wire the farm to the crew and trust the gases to balance. It must hold large reserves of oxygen and carbon dioxide and actively manage the swing between them, buffering one against the other. Or the cabin air will drift too much carbon dioxide here, too little oxygen there toward levels that first dull the mind and then stop the heart. The biological loop does not regulate itself. It has to be flown continuously, like an aircraft that is never allowed to land. And underneath all of it sits the atmosphere itself, which we tend to treat as simply there, and which is in truth one more consumable quietly draining away. Every habitat leaks. No seal is perfect. Air seeps out through fittings and hatches and the walls themselves, molecule by molecule, into the vacuum outside, and every airlock cycle breathes a little more of the colony's atmosphere away forever. That lost air is not only oxygen. Most of what we breathe is nitrogen, an inert gas that fills out the pressure and holds fire in check. And nitrogen, as we have already seen, is one of the most precious and hardest to recover elements the colony owns. So every slow leak of cabin pressure is also a slow leak of the very nitrogen the farm is starving for, vented uselessly out into the surrounding vacuum. The colony must keep topping up its own sky from local sources forever, just to hold the pressure that stands between its people and the vacuum. Even the air around them, the most invisible thing of all, is a tank that is always imperceptibly running down. Why is food so much harder than water? Because of what each one is. Water is a single molecule. Recover the molecule and you are done. Water is water. Food is not one thing. Food is a delivery system for dozens of distinct elements, arranged into specific living structures, in specific forms a body can actually absorb. You do not need nutrients in the abstract. You need nitrogen and phosphorus and potassium and sulfur. You need calcium and iron and zinc and a long list of trace metals. And you need a spread of vitamins, several of which only particular organisms on Earth know how to manufacture. Closing the water loop means recovering one compound. Closing the food loop means recovering and correctly rerouting every single element in the human diet in the right chemical form, into the right organism, in the right order, and doing it without losing any of them along the way. They are not the same difficulty multiplied. They are different problems entirely. Follow nitrogen, because nitrogen is the troublemaker that decides whether the farm lives. Your body sheds nitrogen mostly in urine. A plant cannot use that nitrogen directly. It has to be converted by communities of bacteria into the nitrate form roots can drink. That conversion is exactly what the Melissa loop's microbial stages are built to do, and they do it impressively, recovering on the order of 90% of the nitrogen passing through. Sit with that number though, the same way we sat with the water figure. 90% recovered means 10% lost, every cycle. And nitrogen has a particularly nasty escape route. Certain bacterial reactions turn it back into nitrogen gas, which bubbles harmlessly into the air and out of the biological loop entirely. The atom is not destroyed, it is just useless now, floating in the cabin atmosphere instead of feeding the wheat. Lose 1/10 of your usable nitrogen each turn, and the farm's fertility erodes from underneath it, season after season, no matter how carefully the crew tends the plants. Phosphorus is worse, and it gets less attention because it is undramatic, which is precisely why it is dangerous. Phosphorus is non-negotiable. It is in your bones, in your cell membranes, in the very molecule that carries energy inside every living cell. There is no substitute and no synthesizing your way around a shortage. And the recovery rates are lower than nitrogen in the Melissa work. Phosphorus recovery has run around 3/4, meaning 1/4 of it drops out of circulation every pass, settling into sludges and residues the recyclers cannot reach. A colony can have abundant water, breathable air, and a sky full of energy, and still watch its farms fade, because the phosphorus that builds living tissue is quietly precipitating out of the loop and accumulating as dead waste. It has no way to mine back. The element that everything alive is built from is leaking into the trash. There is one more layer of cruelty in the food problem, and it is the vitamins. Plants are generous, but they are not complete. The clearest example is the vitamin that protects your nerves and builds your blood, the one labelled B12. Plants do not make it. They cannot. In nature, it comes from bacteria, and humans get it through animal products or microbial sources. A colony that imagines it can survive on a pure crop farm is planning, without realizing it, for a slow neurological decline across its whole population. Numbness, anemia, nerve damage arriving quietly over months and years. So the loop cannot be plants alone. It has to include the microbes and possibly the animals that manufacture what plants cannot, which means more organisms, more compartments, more failure points, more places for atoms to leak. Every gap you close in the diet adds complexity, and every bit of complexity adds new cracks for the loop to bleed through. This is also why the romantic image of "they'll just grow food in soil" collapses on contact with reality. The colony does not have soil. Soil is not dirt. Soil is a living institution, a dense ecosystem of bacteria, fungi, and countless microorganisms built up over thousands of years on Earth. And it does the invisible work of cycling nutrients and suppressing disease. A colony cannot pack a functioning soil ecosystem and expect it to stay balanced in a sealed box. The biosphere experiment showed how fast soil microbes can throw the whole system off. So most serious designs lean toward hydroponics growing plants, with their roots bathed in a precisely mixed nutrient solution instead of soil. Hydroponics is efficient and controllable, but it hands the colony a brutal responsibility. There is no living soil to buffer mistakes. The crew must now manufacture the exact chemical recipe of life, balance every element by hand, recover every mineral from the waste stream, and redose it in the right proportion, and do it continuously, forever, with no margin. They have not escaped the leak. They have taken personal, manual ownership of it. And then there is the threat that can erase a season in a week: disease. A closed colony farm is almost certainly a monoculture, or close to it, a small number of crops grown in dense, identical, controlled conditions, which is exactly the environment a plant pathogen dreams of. On Earth, when a blight tears through a crop, farmers reach for fungicides, for resistant seed varieties shipped in from elsewhere, for the deep genetic diversity of the global seed supply. The colony has none of that on call. It cannot order a resistant cultivar. It cannot manufacture a new pesticide without the chemical industry we discussed earlier. If a fungus or a bacterial blight gets into the hydroponic bays and spreads through the genetically uniform crop, the farm can collapse far faster than any new crop can be raised to replace it. And now the food loop and the air loop, which are the same loop, both lurch toward failure at once. The colony does not just need to grow food, It needs to defend a fragile, uniform, irreplaceable ecosystem against an entire microbial world with one hand tied behind its back. And the trouble with a farm is not only that disease can strike it, but that a farm answers slowly to disaster far too slowly for comfort. A machine that breaks can sometimes be fixed in an afternoon. A crop that fails cannot be hurried. If a blight, a lighting failure, a nutrient mistake, or a contamination wipes out a harvest, the colony cannot grow another by morning. A new crop needs weeks or months to mature, and in the meantime, the people still have to eat from whatever store stands between them and hunger. This is why a colony cannot run its farm lean. It must carry a deep buffer of stored food against the near certainty that, somewhere across the decades, a harvest will fail, and it must hold that buffer while also fighting the slow spoilage that eats any stockpile over time. The gap between a crop dying and the next crop ripening is a window of pure vulnerability, and a settlement that has trimmed its margins too far can fall through that window before its fields recover. Worse, the colony cannot grow just anything. It is limited to the handful of crops it thought to bring, and can actually cultivate in a sealed, low-gravity, artificially lit world a short catalogue beside the thousands of species that feed the earth. A narrow menu is a fragile one. Fewer crops mean fewer defences, thinner nutritional coverage, and a heavier dependence on each individual species staying healthy. And the plants themselves are prey to the same quiet decline that threatens the people growing them. Seeds do not store forever. Their ability to sprout fades with the years, and the living seed stock must be continually regrown to stay viable. Each regrowth is a new generation, and each generation, in a small, isolated population of plants, loses a little genetic diversity to the same founder effect that haunts the colonists, drifting, narrowing, slowly forgetting the resilience its ancestors carried. The colony is not only managing a human gene pool across the generations, it is managing a botanical one at the same time, by the same merciless arithmetic, and a crop lineage that thins too far becomes a lineage one bad season away from vanishing, taking with it a piece of the colony's food supply that no warehouse can replace. So let's gather all of this into a single honest picture. Call it the leak ledger. Down one column, list the elements a colony cannot live without: water, carbon, oxygen, nitrogen, phosphorus, potassium, sulfur, and the trace metals and vitamins riding along with them. Next to each, write its recovery rate, and then write what happens to the remainder. Water, around 98% recovered, the rest trapped in brine and biomass and vented vapour. Carbon, leaking out as vented methane and locked into waste solids. Nitrogen, around 90% recovered, the rest escaping as gas into the air. Phosphorus, perhaps 3. Every line of that ledger is a small negative number. And here is the quiet horror of it. The colony can be recycling everything exactly as promised, running its loops at world record efficiency, and still every single element is trending downward. We recycle everything was never a promise of survival. It was a description of a slope. Recycling does not stop the loss, it only slows it. And a leak that is merely slowed is still, given enough years, a leak that empties the tank. And the ledger, for all its grimness, only tracked what drains away. A sealed world has the opposite problem too, and it is just as quiet. Everything inside the habitat is slowly breathing molecules into the air, not the crew, the materials. Plastics, adhesives, insulation, electronics, paints, and the human bodies themselves all give off a faint, ceaseless fog of volatile compounds. Traces of formaldehyde, ammonia, methanol, and a long catalogue of others. On Earth, an entire atmosphere stands ready to dilute that fog to nothing, and we never smell it. In a closed habitat, there is nowhere for any of it to go. So it accumulates a few parts per million, then a few more climbing in the background while every major gauge reads normal. The International Space Station fights this constantly, with a dedicated trace contaminant control system built around beds of activated charcoal and catalytic burners that destroy the worst of the molecules before they reach harmful levels. But notice what those beds are: consumables. They saturate, they exhaust, and they must be replaced on a schedule, exactly like the filters of the water loop. A colony that can no longer replace its contaminant beds does not face a dramatic poisoning. It faces something slower and stranger, its own air gradually turning against it, not through any breach or leak, but through the patient outgassing of the very walls and equipment meant to keep it alive. The danger is not what escapes the loop. It is also what the loop has no way to expel. There is a second invisible population in that sealed world, and the colony's life depends on it even as it is threatened by it. The microbes. A habitat is not sterile, and it must not be, because the settlement leans on microorganisms at every turn. The bacteria that drive the recycling loops, the colonies that convert waste into fertilizer, the unseen ecosystems that make the whole biological cycle turn. But a warm, wet, sealed environment is also a paradise for the microbes nobody wants. Biofilms, slick, layered mats of bacteria creep through the inside of water lines, clogging passages and quietly corroding metal from within. Mold finds the damp surfaces and the hidden corners and takes hold. Orbiting crews have battled recurring mold for decades, scrubbing it back again and again, because in a closed box, it never truly leaves. And over the long run, something more unsettling happens. Microbes evolve, and they evolve fast, generation upon generation, inside the very environment the colony cannot escape, potentially growing more aggressive, more resistant, better adapted to the habitat than the habitat is to them. They are adapting while the crew's defenses are eroding, shared immune systems strained by isolation, and the antibiotics that might have answered them, already aging toward uselessness in the cabinet. The settlement is locked in a contest with an organism that reproduces 1,000,000 times faster than it does, and it cannot resupply its weapons. And the microbial problem reaches inside the colonists themselves, into a place no inventory ever lists. Every human carries a vast internal ecosystem, communities of microbes in the gut that are not passengers but partners, essential to digestion, to immunity, to the manufacture of compounds the body cannot make alone. That inner ecosystem is a living inheritance, seeded and replenished across a lifetime by contact with a whole rich biological world. In a sealed colony, cut off from that world, the human microbiome can drift and narrow, exactly as a closed gene pool does, losing diversity it has no way to restore, generation by generation, as children are born into an ever thinner microbial inheritance than their parents knew. So the colony must keep alive not only its people, its crops, and its recyclers, but the unseen organisms inside and around all of them, a whole hidden layer of life that Earth maintained for free and that cannot be shipped up in a crate. Keeping the colonists fed and breathing, it turns out, was only ever part of the task. The colony also has to keep an entire invisible biosphere in balance, with no Earth left to reseed it from, which forces the colony into the one move that can actually flatten the slope, and it is not a biological move at all. To replace the atoms that escape the nitrogen drifting off as gas, the phosphorus settling into sludge, the carbon venting overboard, the water lost to space, the colony has to find fresh supplies of those elements somewhere in its environment and feed them in to top up the leak. That means mining. It means processing local materials, ice, frozen volatiles, the raw rock and dust of wherever the colony sits to extract water and carbon and nitrogen and the rest, and refining them into forms the loop can use. The field has a name, living off the local land instead of the home planet. And notice what just happened. The biological problem just reached back and grabbed the industrial problem by the collar. To keep the living loop from bleeding out, the colony needs furnaces, chemical extractors, refineries, and the machinery to run them, the very industrial base whose fragility we spent so long establishing. The farm cannot save itself. It needs the factory. And the factory, as we saw, needs spare parts the colony cannot make. The loops are not separate after all. They are choking each other. Be clear-eyed too about how much of this is real versus hoped for, because the honesty is the whole point. What is operating right now, today? On the station, water recovery near 98%, and oxygen generation by electrolysis proven, flying, reliable. What has been demonstrated only at limited scale, on the ground, for a fraction of a crew, the closed biological loops, the European pilot plant feeding part of one person, and decades earlier a Soviet facility called Bios 3 in Krasnoyarsk, which sealed crews inside for up to about 6 months and, using algae and wheat and vegetables, came remarkably close to closing the air and water loops and supplied a large share of the food, though never all of it, and never the full spread of nutrients a body needs. Those were genuine, serious achievements, and they are also the ceiling of what has ever actually been done, what is still under development, recovering the harder elements at high efficiency, closing the nutrient loop for a full, balanced diet, defending closed farms against disease without resupply, and what remains pure extrapolation, demonstrated by no one, a biological loop closed tightly enough at the scale of hundreds of people across decades to lose essentially nothing, topped up by local mining run on locally maintained machines. Nobody has closed the loop on even one person indefinitely. The colony would have to do it for a town. Step back and the shape of the danger comes clear, and it is the answer to the question we have been circling. A colony will not run out of food the way a household runs out of groceries, with empty shelves and an obvious crisis. It will run down the way a body with a slow internal bleed runs down, looking fine, acting fine, the vital signs steady, right up until a threshold is crossed and the decline becomes visible and irreversible all at once. The greenhouses will be green, the water will taste clean, the air will read normal, and underneath it all the phosphorus will be thinning, the nitrogen drifting off, the diet narrowing towards some missing vitamin, the recovery rates that look so triumphant, doing exactly what they always did, slowing the loss without ever stopping it. The most dangerous thing about the biological loop is not that it might break loudly, it is that it can fail silently, while every reassuring number on the wall stays exactly where it should be. But suppose the colony solves it. Suppose, against every difficulty we have laid out, it engineers a loop tight enough and a mining operation good enough to flatten the slope and keep its people fed and breathing for the long haul. Suppose the air is sweet, the harvests are full, the elements stay in balance year after year. Even then, and this is where the next part begins, the colony is not safe. Because we have so far treated the colonists as mouths to feed and lungs to fill, as a load on the system, they are something far more fragile and far more important than that. They are the surgeons who will be needed when someone's appendix bursts and there is no hospital to fly to. They are the engineers who carry, in their own heads, the only working knowledge of how the reactor runs. They are the parents of a generation that must somehow inherit every skill before the people who hold it die. A colony can keep its bodies alive and still lose the one thing it cannot recycle, mine, or print, the people themselves and everything they know. And that loss, it turns out, may arrive long before the food ever runs short. The call comes in the middle of the night. A colonist has doubled over with a pain low on the right side of the abdomen, sharp and worsening by the hour, with a fever climbing behind it. To anyone who has worked in medicine, the picture is grimly familiar. An inflamed appendix, hours from rupture. On Earth, this is one of the most routine emergencies there is. A surgeon makes a small incision, removes the appendix, and the patient is home in a day or two. It is so ordinary that we forget it was a death sentence for most of human history. And in the colony, in that dark hour, it is a death sentence again, unless everything needed to defeat it is already inside the walls. So ask what everything needed actually means, because this is where the real turn comes, and it is a different country from everything before it. Until now, the enemy was physical. Parts that wear out, atoms that leak away, both are problems of matter. But a colony is not only matter, it is people and the knowledge those people carry. And the question of this part is the one nobody likes to face. A base keeps its current residents alive. A civilization keeps the capability to keep people alive across emergencies, across children, across generations. And it turns out a colony can hold its air, its water and its food in perfect balance and still collapse, because the thing that fails first may not be a machine or a nutrient at all. It may be a skill that died with the one person who had it, or a population that quietly slipped below the number it needed to continue. The body of the colony can be healthy while its mind is bleeding out. Return to that appendix. To save this person, the colony needs a trained surgeon who is awake, alive, and not the patient. It needs sterile instruments, anesthesia, antibiotics, and the supporting cast of a working operating room. On Earth, none of that is remarkable. In the colony, Every item on that list is a separate vulnerability, and here is the cruelty unique to a settlement without Earth. There is no evacuation. On the International Space Station, the ultimate medical contingency has always been the ride home, a vehicle docked and ready, capable of returning a sick crew member to a hospital within hours. That escape hatch has quietly underwritten every crewed mission we have ever flown. Remove it, and the calculus inverts completely. The colony cannot send the patient to medicine. All the medicine that will ever exist for that patient must already be present, in that room, in that moment. Evacuation was never a luxury. It was a hidden layer of the entire medical system, and the colony does not have it. Now consider the antibiotics. Because they expose a trap the colony cannot engineer its way out of. Drugs are not permanent, they degrade. Every medication carries an expiration date, because its molecules slowly break down, and many lose potency within a few years even in good storage. A colony cut off from Earth is therefore not just rationing a fixed stockpile of medicine, it is racing a clock that is ticking on the stockpile itself. The pills are dying in the cabinet whether or not anyone is sick, and you cannot simply manufacture more, because making a modern pharmaceutical is not cooking. It is the end product of exactly the chemical industry we already watched. The colony failed to carry feedstocks, reactors, catalysts, purification, quality control, the works. A complex antibiotic or anesthetic involves dozens of synthesis steps and reagents that the colony has no way to produce. So the day comes when the last effective dose of a critical drug expires, and there is no next batch, and a category of illness that medicine had conquered for 2 centuries becomes lethal again inside the colony walls. The settlement does not lose medicine in a dramatic event. It watches its pharmacy quietly expire, and the appendix is only the gentlest example. Run down the ordinary catalogue of what a human body does over a lifetime, and each entry becomes a crisis without Earth behind it. A difficult childbirth routine on Earth, and for nearly all of human history a leading cause of death now unfolds with no specialist hospital to call upon, no blood bank, no surgical team on standby, and the colony's very future riding on the outcome, since these are the births that make the next generation. A tooth abscesses, and without a dentist and the slow chain of dental supplies behind one, an infection in the mouth can spread into something that kills. A bone breaks badly, a wound turns septic, a cancer takes hold that on Earth would be survivable. And threaded through every one of these is the same vanishing resource: anesthesia, the ability to render a person safely unconscious, or to numb a region while you work, is a quiet miracle of modern chemistry, and those compounds expire and cannot be resynthesized without the chemical industry the colony does not have. A settlement that runs out of the means to manage pain has not merely lost a comfort. It has slipped backward into an age when surgery meant agony, and the surgeon worked against a screaming clock, except now without even the deep institutional knowledge that age had painfully accumulated. This is the first hard distinction worth holding, and it reframes the whole question of survival. Keeping someone alive is not the same as keeping the ability to keep people alive. A colony can stock enough medicine and enough trained people to handle the first decade beautifully and still have made no provision at all for the second. When the drugs are gone, the equipment has worn out, and the original doctors are aging. Survival measured in residents is a snapshot. Survival measured in capability is a movie. And the movie has a much darker ending if no one is recreating the medicine, the tools, and the expertise as fast as they decay. Which brings us to the most fragile and least visible resource the colony owns: skill. Not knowledge written down skill, living in human heads and hands. Think about who actually keeps the colony alive on a normal Tuesday. There is someone who understands the power system at a level deeper than any manual, who can hear a fault before the sensors catch it. There is someone who knows the bioreactor's moods, who can coax the microbial loop back into balance when it drifts. There is the surgeon, the machinist, the chemist, the electronics technician. In a small colony, for any given critical system, that expertise might live in a single mind or two, and a single mind is mortal. It can die in an accident, fall ill, age out, or simply burn out and lose the edge. When it goes, the capability does not degrade gracefully. It vanishes. The reactor still hums, but now no one truly understands it. And the colony is running a system it can operate but no longer comprehend fine until the day it isn't. And then catastrophically not fine, with no one left who knows why. People reach instinctively for the obvious fix. Write it all down, store the knowledge, carry a vast digital library, every textbook, every manual, every repair procedure humanity has ever produced, and the problem dissolves. But it does not. And understanding why is central to everything here. A document is not a skill. Reading every book ever written about surgery does not make you able to open a living abdomen, find the inflamed appendix among the glistening organs, and close the wound without killing the patient. Surgery is judgment under pressure, built from years of supervised practice, hands guided by other hands. The same is true of welding a critical seam, of diagnosing a sick power system by feel, of running a chemical synthesis where the difference between medicine and poison is a matter of experience technique. Knowledge can be stored. Skill must be transferred, taught, demonstrated, practiced, corrected, from a person who has it to a person who does not. The library is necessary, but it is inert. It is the difference between owning the sheet music and being able to play. So education stops being a quality of life amenity and becomes life support in the most literal sense. The colony does not merely need to keep its experts alive, it needs to copy them. Every critical skill must be deliberately reproduced in the next generation, before the people who hold it are gone, and reproduced not once, but redundantly, in several people, so the loss of any single mind is survivable. This is a staggering burden for a small population. A surgeon must train new surgeons while also being the surgeon. A master machinist must teach machining while keeping the machines running. The colony is trying to operate a civilization and run an apprenticeship for that entire civilization at the same time, with a tiny number of teachers and an unforgiving deadline measured in human lifespans. If even one essential skill fails to make the jump to the next generation, if the chain of teaching breaks for a single trade, that capability is gone, and unlike a spare part, you cannot order it from a shelf, because the shelf was a person, and the person is dead. And teaching, it turns out, is not free either. It costs the one resource a small colony has least of: time, measured in human hours. Mastery of a real craft is not a weekend course. To make a competent surgeon, a true machinist, a chemist who can be trusted with the colony's medicine, takes years of patient, supervised practice, a decade of someone's life. Sometimes more, much of it spent learning at the elbow of a person who already knows. But in a settlement where every adult is already doing the work of 2 or 3 people, who has those years to spare? The same expert who must keep the reactor running is the only one who can teach the next person to run it, and there are only so many hours in a day. The teacher cannot teach and operate at the same time, and the student cannot reach mastery while also pulling a full share of the labour that keeps everyone alive. So the colony is caught in a vice made of arithmetic. It needs to reproduce every essential skill redundantly in a new generation, and it may simply not contain enough teaching hours to do it. Skills take time to transfer that a survival-stretched population does not have, and a craft that cannot be taught deeply enough to enough people before its holder ages out is a craft already half lost. A settlement can be full of willing, capable young people and still fail to pass on what it knows, not for any lack of intelligence or effort, but because there were never enough hands and never enough hours to teach everything that had to be taught while also staying alive. And this assumes there is a next generation which opens onto the deepest constraint of all, the one that operates on a timescale longer than any individual life, the population itself, and the merciless arithmetic of genetics. A colony that intends to last centuries must do something no space crew has ever done: reproduce, generation after generation, in isolation. And reproduction in a small, closed group runs straight into a wall that conservation biologists know intimately: the founder effect and inbreeding depression. When a population starts from a small number of founders, it carries only a thin slice of the genetic variety of the species it came from. As that small group interbreeds over generations, harmful recessive traits that are normally rare get concentrated, surface more often, and accumulate. Genetic diversity erodes. Health declines. Fertility can fall, The population can spiral downward not because of any external threat, but because the math of small numbers turned inward on itself. This is not speculation. Earth has run the experiment repeatedly, in the open air, and the results are written into real human populations. Iceland was settled roughly 11 centuries ago by something on the order of 10,000 people, and even from that not tiny founding stock, the modern population remains one of the least genetically diverse in Europe, diverse enough to thrive, but a clear fingerprint of the founder effect at work. The more pointed example sits in the remote South Atlantic, an island called Tristan da Cunha, settled in the early 1800s by a mere handful of people. Generations of necessary intermarriage among the descendants of those few founders concentrated specific inherited conditions in the population to a degree far above the global norm. These are not curiosities. They are direct, measured demonstrations of what happens when human beings try to build a lasting population from too few starting genes. A colony that gets this number wrong is not risking discomfort. It is risking a slow genetic decline it cannot reverse, because it has no way to import fresh diversity from outside. So what is the right number? Here the honesty of the science matters, because the estimates vary enormously, and that variation is itself the lesson. Conservation biology offers a famous rule of thumb, sometimes summarized as 50 in the short term, 500 in the long term, meaning you need on the order of 50 breeding individuals just to avoid immediate inbreeding harm, and on the order of 500 to retain enough diversity to keep adapting over the long haul. But notice that 500 is an effective breeding number, not a total population. Once you account for children, the elderly, and uneven reproduction, the real headcount required is considerably larger. When researchers modelled this specifically for multi-generational space voyages, the numbers spread across a wide and sobering range. One early study suggested a founding crew of roughly 150 to a few hundred might suffice under ideal, tightly managed mating conditions. A later and more cautious analysis, accounting for mutation, genetic drift, and the near certainty of at least one population catastrophe along the way, argued you would need a founding population in the range of 14,000 to 44,000 people to stay genuinely healthy across the generations. Other simulations, by relaxing the rules and managing reproduction cleverly, push the minimum back down toward the low thousands or even hundreds. The colony cannot afford to be wrong about which estimate is right, and that uncertainty is the point. If the true number needed for long-term genetic health is several thousand, then a romantic outpost of a few hundred pioneers is not a seed of a new branch of humanity. It is a population that looks vigorous in its first generation and is already, invisibly, on a genetic slope toward decline, the same pattern we keep meeting, where the danger is real long before it is visible. There are partial technological patches, and we should be honest about their status. Stored genetic material, frozen embryos, banked eggs and sperm, representing a wide range of donors, is a real and demonstrated technology, and it could inject diversity that the living founders alone could never supply, effectively letting a smaller colony behave genetically like a larger one. More speculative, and far from solved, is the idea of directly editing genomes to repair concentrated defects or restore lost diversity. The first is a genuine tool the colony might carry. The second is a hope, not a capability. Neither erases the fundamental truth. A colony's long-term survival is constrained not just by how many people it can feed today, but by how many distinct genomes it brought, and how carefully it manages the unforgiving genetics of a closed gene pool. Layered on top of the genetic math is a more immediate demographic fragility, and it is brutal in its simplicity. A small population is a population with no buffer. On Earth, a town of 300 can absorb the loss of 10 people to an accident or an outbreak. It grieves, and it goes on. In a closed colony, those same 10 deaths might wipe out the only surgeon, the only reactor specialist, 2 of the 3 people who understood the farm, and a slice of the reproductive core all at once, a blow to capability and to the gene pool simultaneously. A single epidemic sweeping through a confined habitat, a single decompression accident, a single fire in the wrong module can knock a small colony below the threshold it needs to continue not just to grow, but to maintain itself and its skills, and age structure matters as much as raw numbers. A colony, top-heavy with aging experts and short on children, is a colony watching its capability and its future drain away at the same time, with the teachers dying faster than the students can replace them. Demographics is not a soft background variable. It is a hard limit that can end the colony in an afternoon. We have not yet mentioned the threat that works on the longest clock of all, quietly shaping every one of these problems: radiation. It is tempting to picture radiation as a sudden killer, and a severe burst from a solar storm genuinely can be, which is why any serious colony needs heavily shielded shelters, walls of water or rock or local soil thick enough to blunt the worst of it, because those particles are stopped by mass and nothing else. But the more insidious threat is not the dramatic burst. It is the steady, grinding background of cosmic radiation that seeps through the habitat day after day, year after year. This is not an acute injury. It is a slow accumulation, a rising lifetime dose that raises the long-term odds of cancer, that can damage the nervous system over decades, and, most consequentially for a multi-generational colony, that can harm reproductive cells and accumulate genetic damage passed from parents to children. Radiation, in other words, is not only a medical problem for the living, it is a long-term tax on the very gene pool the colony is straining to protect, compounding the genetic fragility we just walked through. Shielding can reduce it, never eliminate it, and every gram of shielding is mass and structure that itself must be maintained. Then there is the layer that no engineering diagram contains, and that may decide everything. The colonists are not just bodies and skill sets and genomes. They are people, locked together for life, with no exit. Consider what that means psychologically. There is no leaving. There is no transfer to another city, no walking away from a feud, no fresh start somewhere else. Every relationship, every grievance, every personality clash is permanent and inescapable, lived out in a confined space among the same faces for decades. The history of isolated and confined human groups, polar stations, submarines, long expeditions, shows how quickly morale, cohesion, and mental health can fray under exactly these conditions. And those groups always had an end date and a way home. The colony has neither. Depression, conflict, the slow corrosion of shared purpose. These are not soft concerns, layered on top of the survival problem. In a settlement where a handful of skilled minds are irreplaceable, the psychological collapse or violent loss of even a few key people is a survival problem of the first order. A brilliant engineer who breaks down is as gone, functionally, as one who dies. And surrounding all of it is the question of how the colony governs itself, how it makes decisions, resolves disputes, and holds together as an institution across generations. This is not a political aside, it is load-bearing. The systems we have described demand discipline that never lapses, the relentless education of every new generation, the careful management of who reproduces with whom, the maintenance schedules that cannot be skipped, the rationing of irreplaceable spares, the response to emergencies. All of that requires a stable social order capable of enforcing long-term commitments against short-term temptation and capable of surviving its own leadership transitions without tearing apart. Institutions are a kind of life support system too, and like the others, they can fail silently. A colony does not need a war to collapse its governance. It only needs the slow erosion of cooperation, the breakdown of the agreements that keep the schools running and the experts teaching and the reproductive program managed, and once those agreements fray, every other system we have discussed begins to fray with them, because every other system depends on people choosing, year after year, to keep doing the hard, disciplined, unglamorous work of continuation. And there is one more fracture line, unique to a colony built to last, that no founding crew can consent away on behalf of the people it matters most to, the second generation. The first colonists chose this. They volunteered, they trained, they accepted the danger and the confinement with open eyes. Their children did not. They are simply born into a sealed world they never agreed to, handed a life of relentless duty, the endless maintenance, the managed reproduction, the rationed spares, the inescapable closeness without ever having been asked. And human beings do not reliably inherit their parents' sense of mission. The drive that carried the founders across the dark can thin in the children and thin further in the grandchildren until the discipline the whole settlement depends on begins to feel less like a shared purpose and more like a sentence. With it goes the legitimacy of authority itself. It is one thing for volunteers to accept hard rules they chose, and quite another to enforce those same rules on people who were born under them and want out. A colony can keep its bodies alive, its loops closed, and its gene pool managed, and still come apart at this exact seam, because the systems of survival demand obedience and effort across generations, and somewhere down the line a generation may simply decide that it never signed up to keep paying. Pull these threads together, and the central clarification comes into focus, and it is a hierarchy of survival that the word survival usually hides. Keeping the first residents alive is the easiest tier. Bring enough supplies and skilled people, and you can do it for years. Supporting children actually producing and raising a healthy next generation is a harder tier, gated by genetics, demographics, and the radiation tax on the gene pool. Surviving an emergency without the safety net of evacuation is a different tier again, gated by medicine that expires and expertise that can die in a single accident. And remaining genuinely capable across centuries, still able to make medicine, still able to teach surgery, still able to maintain a viable population and a functioning society, is the highest tier of all, and it is the one that almost everything works against. A colony can clear the first tier with ease and never come close to the last. And a colony that has only cleared the first tier, while believing it has cleared them all, is not surviving in any lasting sense. It is merely delaying its collapse and calling the delay success. Because watch how each of these failures actually presents itself, and you will recognize the pattern that has haunted every step of this story. The medicine does not vanish in a crisis. It quietly expires in the cabinet. The skill does not announce its departure. It dies with a person, and the gap is only discovered the day it is needed. The gene pool does not crash on a schedule. It thins, generation by generation, invisible until a threshold is crossed. The society does not fall in a single dramatic act. It erodes, agreement by agreement, until the schools stop and the teaching stops and no one quite remembers when. In every case, the colony can look healthy clinics busy, classrooms full, this year's emergencies handled while it has already, silently, begun to lose the capabilities it will never get back. The surgery goes well and the lessons get taught and the medicine still works today, and none of that tells you whether the colony can still do any of it in 50 years when the original experts are dead and the original drugs are dust. So we arrive at the edge of the real question, the one everything so far has been driving toward. Keeping bodies alive, we have seen, the colony might manage. Keeping the loop of matter closed, with enough ingenuity and local mining, it might manage. Keeping people and skills and a gene pool alive across generations with ferocious discipline, it might just manage too. But every one of those depends, in the end, on the same thing, the ability to remake what is lost faster than it is lost. To make new medicine, you need a chemical industry. To teach new surgeons, you need a medical and educational infrastructure. To run the mines that top up the leaking loop, you need the machines and the power and the raw materials to keep them running. Survival, it turns out, is not a matter of stockpiles or even of people. It is a matter of whether the colony can rebuild, from scratch and forever, the entire industrial and intellectual ecosystem that Earth once provided for free and that no one ever thought to count. That capacity, the full machinery of a self-sustaining civilization, is the final threshold, the line that separates a colony that is truly surviving from one that is only, very slowly and very quietly, running out. And measuring that threshold, naming exactly what it would take to cross it, is where this story finally has to end. Cut the power for a moment. Not for long, just a single hour, across the entire colony, and watch what the darkness reveals. The lights go first, of course, but the lights are the smallest part of it. In that one dark hour, the air handlers stop pushing oxygen through the corridors. The machine splitting water into breathable air falls silent. The recyclers stop turning waste back into water. The pumps stop. The heaters that hold the farm at growing temperature go cold, and so does the refrigeration that keeps the medicine from spoiling and the frozen genetic bank from thawing. The carbon dioxide scrubbers quit, and the very air the crew is breathing begins, slowly, to turn against them. Every single system we have spent 3 parts describing the machines: the loops, the food, the medicine, the cold storage of the colony's own future, turns out to have been running on one invisible thing. And when that one thing stops, they do not fail one at a time. They fail together, in the same instant, holding their breath in the dark. This is the truth all of this is built on, and it reorganizes everything that came before it. Energy is not one system among many. Energy is the master variable, the thing every other system is secretly made of. Look closely at any loop in the colony, and you find the same secret underneath. Recycling water is a way of spending energy. Generating oxygen is a way of spending energy. Growing food under lights, melting metal to cast a part, synthesizing a drug, keeping a habitat warm against the cold outside. All of it is energy, wearing different costumes. A colony does not really run on water and food and spare parts. It runs on watts. Water and food and spare parts are just watts in another shape. And that means the question of how long a colony can survive collapses, in the end, into a question about power. How much it can generate, how reliably, and for how long. Picture the colony then as a valley full of mills, every wheel turning on a single current. The farm wheel, the air wheel, the water wheel, the workshop wheel, the medical wheel, all of them turn because the current keeps flowing. On Earth, the current is so dependable we forget it is there. Behind every wall socket stands a continental grid, thousands of power plants, a whole industry whose only job is to make sure the current never stops. The colony has no continent behind its wall. It has one source, or perhaps 2, and behind those, nothing. So energy redundancy is not a comfort for the colony. It is the difference between life and a single point of total failure, because if the power has no backup, then a fault in the power plant is not the loss of one wheel. It is the loss of every wheel in the valley at once, which is the one failure no amount of food or spares or skill can survive, not even for the length of an afternoon. So how does the colony make its current, and can it keep making it? 2 paths dominate, and both lead back to the same problem. The first is sunlight. Spread enough panels and you can drink power straight from the local star, clean, abundant, with no fuel to run out. But sunlight is not a guarantee. It vanishes every night, weakens with distance from the star, and can be smothered for weeks by dust. And the panels themselves are not eternal. They degrade year over year. They crack, they foul, and the colony cannot fabricate new ones, because a solar panel is a semiconductor product born of the same fabrication plants the colony could never carry. The second path is nuclear, a reactor splitting heavy atoms to make heat and then power, indifferent to night or dust or distance. Small fission reactors for space are real, but they have been tested only at limited experimental scale, never as the multi-generational, self-maintaining power plant a colony would need. A reactor's fuel is finite, its parts wear, and maintaining one demands exactly the industrial base we are still trying to establish. And between either source and the colony sits a third weakness that is easy to overlook: storage. Power has to be saved for the dark hours, the long night, the dust-smothered week, the gap between a fault and its repair, and that saving is done in batteries or other reserves that only ever empty and never refill themselves. Every charge and discharge wears them a little. Their capacity fades cycle by cycle until they hold a fraction of what they once did, and the colony cannot fabricate fresh ones. A settlement can be generating power and still go dark, because the vessel meant to hold it through the night has quietly worn out. Whichever path the colony takes, the lesson is identical. The means of making energy is itself hardware, and hardware, as we learned at the very beginning of this story, has a lifespan. Energy is not only what the colony must spend, it is something the colony must keep being able to produce, against the same wear that grinds down everything else. But suppose the colony solves power. Suppose it has redundant reactors, deep fuel reserves, every watt it could want, forever. It is still not safe because energy only lets you run machines. It does not give you the machines. And here we arrive at the deepest structure in the entire problem, the thing that decides whether independence is even possible: the industrial pyramid. Every capability the colony has sits on top of other capabilities. To make a replacement part, you need a tool. To make that tool, you need another tool, and a material, and a process, and each of those rests on something beneath it. The whole of industrial civilization is this capability stacked on capability, all the way down to raw rock and raw energy. And the question that determines the colony's fate is whether there exists a bottom to that stack that can reach back up and rebuild the whole thing. A minimum self-replicating industrial base. The smallest complete set of tools, machines, materials, and skills that can reproduce every part of itself, including its own tools from local resources alone. This is one of the oldest and strangest questions in science, and it has a name attached to it. In the middle of the last century, the mathematician John von Neumann asked whether a machine could build a complete working copy of itself, not just a part, but the whole thing, including the part of the machine that copies the blueprint. He showed, on paper, that it was logically possible. Then, in 1980, a NASA summer study took the idea from pure theory toward engineering and sketched something audacious: a self-replicating factory. A seed of roughly 100 tons of machinery that, set down on a barren world and fed nothing but local material and sunlight, might, by the study's own estimate, build a full copy of itself in roughly a year, and then those two could build two more, and the base could grow without another gram shipped from home. If such a thing could be built, the colony's whole crisis would dissolve. It could simply grow its own industry, the way a forest grows trees. But notice the words "on paper" and "in principle," because they carry the entire weight of the question. Not one self-replicating factory has ever been built, not on Earth, not in space, not anywhere, not even close. We do not possess machines that can make all of their own parts. The most automated, most advanced factory on Earth still sits at the end of a supply chain that wraps around the whole planet, drawing in chips and bearings and chemicals and tools from thousands of other factories it could never reproduce. The self-replicating factory is a beautiful idea, and an unbuilt one, and a colony cannot bet its survival on a machine that has never existed. And here lies the exact trap the honest version of this story has to refuse. It is tempting at this point to wave a hand at automation and artificial intelligence, and say the robots will simply handle it, that a clever enough system will close the whole loop for us. But intelligence was never the bottleneck. Knowing how to make a precision bearing is not the same as possessing the foundry, the alloy, the furnace, and the tools to actually make one. A brilliant mind, or a brilliant machine, standing in a room with no industry behind it makes nothing at all. The pyramid is physical, not mental. No amount of cleverness lets you skip a tier of it. You cannot think a chip fabrication plant into existence. So the colony is left facing a number it cannot argue its way around. How complete does its industrial base have to be before it counts as truly self-sustaining? And the answer, when you follow every thread of the previous parts, is brutal. To remake everything it depends on, the colony would need, in miniature, very nearly the whole of Earth's industrial economy: mining, refining, metalworking, chemical synthesis, precision machining, electronics fabrication, pharmaceutical chemistry, and the tools and skills to maintain every one of them. And here is the cruelty of a pyramid. You do not get partial credit. A colony that has rebuilt 90% of Earth's industry is not 90% independent. It is still completely dependent, because the missing 10% is precisely the part it cannot live without, and cannot make the chip that runs the life support controller, the drug that stops the infection, the alloy that survives the reactor. Independence is not a percentage you can creep up on. It is a threshold. Either the loop closes, or it does not. And a loop that is 99% closed is in the end an open loop with a slower leak. And even a complete set of machines is not enough, because machines eat raw material, and raw material has to come from somewhere. This is where the colony's reliance on local mining stops being an occasional patch for a leak and becomes a permanent, full-scale extractive industry, quarrying rock, cracking ice, refining metals, fixing carbon and nitrogen, running foundries and chemical plants around the clock, forever, just to feed the factories that feed the colony. But there is a catch beneath even this, and it is the most unforgiving constraint of all, because no engineering can overcome it. The colony can only mine what the ground beneath it actually contains. Earth's crust is a particular and extraordinarily generous mixture, holding nearly every element a technological species could ever want, in reachable concentrations. The rock the colony happens to sit on may not be so kind. A given moon or asteroid or planet might be rich in iron and silicon and starved of phosphorus, or full of metals and bone dry of the carbon and nitrogen that life is built from, or missing entirely some trace element that the colony's electronics or its biology cannot do without. With boundless energy and a perfect factory, the colony can still hit a wall made of simple chemistry. The element is not there is no ship to import it, and the periodic table the colony can actually reach was fixed forever the day it chose where to land. Geology becomes destiny. Where you settle decides what you can ever build. Suppose, against all of this, the colony has it all: the power, the complete pyramid, the rich and obliging geology. It is still not finished, because a self-sustaining system needs one more thing that does not show up in any inventory: depth, redundancy, no single point whose failure takes down the whole. On Earth, redundancy is invisible and free. If one factory burns, 1,000 others keep producing, and no one outside the gates even notices. The colony enjoys no such cushion. It has to build its redundancy on purpose and pay for every gram of it 2 reactors instead of 1, 2 of every critical fabrication line, several people trained in each essential skill so that no capability lives in a single mortal head. This runs against every instinct toward efficiency, and that tension is itself a quiet lesson. A truly self-sufficient civilization is not a lean machine. It is a deliberately, almost wastefully redundant one, carrying spare capacity it hopes never to use, precisely because the moment it trims itself down to the elegant minimum, a single ordinary failure becomes fatal. The colony that optimizes itself for efficiency is, without realizing it, optimizing itself toward fragility. Slack is not waste here. Slack is survival. And beneath all of it, the energy, the pyramid, the materials, the redundancy, sits the layer that animates the rest and cannot be stockpiled at all: living knowledge. We established earlier that a skill is not the same as a stored instruction, that it has to be taught from one person to another or it simply ceases to exist. At the scale of a whole civilization, the demand goes further still. The colony cannot merely keep operators who can follow inherited procedures. It has to preserve the deeper understanding that lets people redesign and reinvent, to grasp the underlying chemistry well enough to find a new synthesis route when the old ingredients run out, to understand the physics of the reactor well enough to engineer a fix the manual never anticipated. A civilization that can only repeat what it was taught is brittle. The first genuinely new problem, the first failure no procedure covers, defeats it. True independence requires keeping alive the rarest and most fragile capability of all the capacity to innovate inside a small, isolated, pressured population, across centuries, with no fresh minds arriving from outside to refill the well of ideas. That is harder than any reactor. So now we can finally state the thing this entire story has been building toward, plainly and without hedging. A deep space colony does not survive by carrying enough. There is no enough. No stockpile is deep enough to outlast the wear of decades, the slow bleed of elements from the loop, the death of irreplaceable skills, the thinning of a closed gene pool. A colony survives only if it can continually repair, reproduce, and recreate the systems of civilization from within its machines, its loops, its medicines, its people, and its knowledge faster than time takes them apart. Survival, it turns out, was never a quantity at all. It is a process. It is not measured by what the colony has. It is measured by what the colony can remake, which lets us name, at last, the true survival threshold. And it is not the one anyone packs the cargo holds to meet. It is not the size of the food store, or the number of spare seals in the locker, or the depth of the medicine cabinet. The threshold of true independence is whether the colony can replace Earth. Not Earth as a place, but Earth as a function. Because Earth was never merely a warehouse that shipped out supplies. Earth was a living industrial ecosystem, a self-feeding, self-repairing, self-reproducing system of industry, agriculture, medicine, knowledge, and population that regenerated itself endlessly without any single mind directing it to. That ecosystem was the real life support system all along. The food shipments and the spare parts and the doctors were only its visible outputs, the steam off the surface of something vast and mostly unseen. To survive for generations rather than years, the colony would have to become a second one of these ecosystems, complete enough, deep enough, and self-renewing enough that it loses nothing it cannot remake. Anything short of that is not a home. It is a countdown wearing a home's clothing. And here, at the very end, we have to be honest about how that countdown actually runs out, because it is not the ending anyone pictures. We imagine the death of a colony as a catastrophe. The breach, the fire, the explosion, the single terrible day everyone could point to afterward. But the strange logic of everything we have traced is that catastrophe is the survivable kind of failure. A blowout, a blight, a fire, these are loud, and a colony with real redundancy and real skill is built precisely to absorb loud failures and recover. The failures that truly end a colony make no sound at all. They are the silent ones this whole story has followed from the start. The last spare quietly slotted into place. The last dose of a drug quietly slipping past the date when it still worked. The last person who genuinely understood a system quietly dying in their sleep. The last unrepeated thread of genetic diversity quietly thinning out of the population. The last mind capable of reinventing a lost process, quietly deciding the problem is too hard. Not one of those rings an alarm. Not one of them moves a needle on any gauge on any wall. So picture the colony at what looks like its golden hour. The greenhouses hang heavy with fruit. The reactor hums, steady and warm. A third generation of children, born under another star, laughs somewhere down a bright corridor. The water is clean, the air is sweet, the lights are strong. By every measure a visitor could see, the settlement is not merely surviving, it is flourishing. And yet, in a workshop no one has opened in years, the single machine that could cut one particular precision part has finally worn past use, and the one person who knew how to rebuild that machine has been dead for a decade. And no one has noticed, because that part has not happened to fail yet. The capability is already gone. The colony simply does not know it. It is living, healthy and untroubled, inside the gap between losing something and discovering that it is lost. And that gap can last for years, even generations, right up until the day the part is finally needed and the terrible, quiet truth surfaces that there is no longer anyone and no longer any machine that can make it. That is where this question leaves us, and it is not a tidy place. A deep space colony would not survive simply by carrying enough supplies, and it would not die on a clean, predictable date that anyone could circle on a calendar. It would live exactly as long as it could keep remaking itself, and not 1 hour longer. And in the cruelest twist of all, it could appear perfectly, radiantly alive long after it had already begun, invisibly, to lose the very capabilities that made survival possible. The harvest still comes in, the lights still burn, and somewhere down the hall a single candle at the far dark end goes quietly out, and the room is still bright enough that no one thinks to turn and look. The real measure of a colony's survival was never how much of Earth it remembered to carry into the dark. It was whether it could become Earth, a whole living world, endlessly rebuilding itself before it forgot, one silent loss at a time, how.